So we continue from the previous video. We have defined u in terms of a differentiation in terms of the beta. That's what we did in the last video, equation number 3. And what was our intention? Our intention was to connect it to some kind of a what of a thermodynamic parameter. Here actually the u can be also written minus dou, the u is equal to minus dou by dou beta of ln q, right? So this is another way of writing the same thing. Depending on the situation, you can utilize all these equations for solving some problems. So keep all these things in mind. So it's important to learn each of these steps so that you can utilize it at any point of time. Some equations may be simplified to use when you are expressing in terms of minus dou by dou beta of ln q, which gives you the energy, the average energy. So what is the u is here? This is the u. This is the average energy of the element of an ensemble. Right. So Helmholtz free energy A is equal to u minus ts. So we are trying to make the connection with A, right? So A is equal to u minus ts. Therefore, I can write u is equal to we will therefore u is equal to A plus ts, right? Which can be, we will convert this S to be expressed in terms of A. So for that purpose, based on this expression, I can always write S is equal to minus dou A by dou T, right? So if I substitute over here, this can be written as A plus, sorry, A minus, because A plus Ts, but here we substitute that, so A minus T into dou A by dou T, which can be expressed in terms of, we can rearrange it, that differentiation, and we can write this as minus T squared into dou by dou T of A by T. Dou by dou T of A by T, which can be again written as dou of A by T divided by dou of 1 by T. These are equivalents. So if I do this one, I will get this one, right? Minus T squared. So dou by dou of 1 by T, dou of A by T. So if I do this one, I will get this minus T squared. So I just wrote it according to my convenience. So if I now this is equal, this was u, right? So u is equal to this one, u is equal to this one. So if I compare this one, I can, so both I equate the right hand sides of the equation number 3 and equation number 5. So what will I get? Dou of A by T divided by dou of 1 by T is equal to minus of dou by dou beta ln sum over r exponential minus beta er. Or I supply k in the denominator of the left hand sides, denominators of the left hand side. So which I can write it as dou of a by kt divided by dou of 1 by kt is equal to minus dou by dou beta ln of sum over r exponential minus beta er. Right? But we know that beta is equal to 1 by kt. Therefore, in that case, we can write this as, right, a by kt is equal to minus ln summation over r. Right? 1 by kt is beta. So therefore I can write always like this. A by kt. If I equate this one, so a by kt is equal to minus ln exponential minus beta er. Or I can write a is equal to minus of kt ln summation over r exponential minus beta er, or minus kt ln qn. So that is it. So that was our aim, to make a connection between a and the q, and we have made it. A is equal to minus kt ln qn. Okay. So if we the relevance is that I have told you in detail the kind of significance of the partition function in defining any statistical mechanic system, right? So therefore, and also I told you that Qn, or the partition function, forms the fingerprint which decides the statistical mechanical system. So the moment you have the partition function evaluated through theoretical means, then we can compute the corresponding all the thermodynamic parameters with the help of this expression, A is equal to minus kt ln qn. And in one of the previous classes, I have listed a number of equations connecting the thermodynamic parameters with each other, right? So the moment you have the A calculated, you can calculate a whole lot of thermodynamic parameters using this expression. So that's the idea. And another question which we were trying to address in the beginning was whether the Qn is an extensive parameter. So this equation again proves that Qn, or the partition function, is a extensive parameter, right? Why? Because since A is an extensive parameter, Qn is also an extensive parameter. Okay. So that is it. So we know one of the other than the kind of features which I told about the partition function. And so now we know one more feature, that Qn is a partition function. So the Qn is Qn, or the partition function, is also an extensive parameter. So A is equal to minus kt ln qn. So by heart this one, and be aware of the derivation. We will continue more about the canonical ensemble in the next video.